Good evening, everyone. Thanks for coming to the talk. This is a joint work with some amazing set of collaborators, Srinadh, Bhojanapalli, okay, Nicolas, Boumal, Praneeth, Netrapalli. So in this talk, I will discuss semi-definite programming, and in particular, this form of semi-definite programs, where the goal is to find a positive semi-definite matrix X that satisfies a bunch of linear constraints and optimizes a linear objective function. Now, I'm sure I don't need to convince this audience that SDPs are really critical for various applications, and we need to develop polynomial or efficient algorithms for this problem, especially in settings where the number of variables can be very large. We have several existing polynomial time algorithms for this problem, but for various cases, for various settings, especially when the number of variables or number of constraints can be large, some of these solutions can be inefficient. So one big source of inefficiency comes because of this PSD constraint. That is, because these algorithms tend to be iterative, they need to maintain that the iterate is positive semi-definite, because of which they will compute eigenvalue decomposition of the matrix to project it back onto the set of PSD matrices. And that can be expensive in general. So one easy way of getting rid of this issue is to factorize the matrix X. That is, if you write matrix X as U times U transpose, then we know that by default, it will satisfy PSD constraint. And you can write then the optimization problem in U. In this work, we'll focus only on a penalty version of this problem, where we take all these constraints and put it in the objective function. So if mu is large enough, then the optimal solution of this will correspond to the optimal solution of this problem. Okay. So now a nice advantage of this factorization is that rather than working with U, which is full rank, that is n by n matrix, now you can think of U matrices to be very thin. That is, let's say U has only k columns. That is, the rank of this matrix X is going to be at most k. And because of this low rank structure, now our algorithm might be able to save on memory as well as compute. Moreover, in several downstream applications like matrix completion, we actually want a low-rank solution to this problem so that we can compute various things efficiently. Right? So now, naturally, a big question here is that how small can we set this parameter k to be? Because that controls the efficiency of our algorithm. So it turns out that for any arbitrary feasible SDP, with m constraints, you can set this parameter k to be at most root of 2m. And this is a tight bound. So this says that you give me any SDP with m constraints, I can run this factorization approach with rank root 2m. And if I can solve the problem optimally, then I would have achieved a global optima. But the issue is that this factorization problem is non-convex. And in general, we know only of efficient algorithms for solving such non-convex problems up to second order stationary point. That is, we might end up with stationary points which are second order and can be far away from the global optimum. Right? So my co-author, Nicolas, Boumal, and some of his colleagues showed that this is not the case for a large class of SDPs. So if, let's say, this SDP is what we call smooth, that is where this matrix C is intuitively random, then the second order stationary point of this problem corresponds to the global optima, every single second order stationary point. So that's great. But unfortunately, there are several interesting SDPs which are not smooth. That is, where this cost matrix can be far away from random. Moreover, in practice, we won't be able to solve a problem of this type up to exactly. That is, we won't be able to obtain exact second order stationary point. We might be able to obtain only approximate second order stationary point, in which case, again, the existing theory might not hold. So in this work, we get around this issue by using this approach of smooth analysis, which is very popular in TCS community. For several problems in TCS community, to avoid the worst case instance, which can break this entire theory, you add little bit of perturbation and then try to do the analysis with the perturb problem. And that's what we will do here. That is, we will try to avoid this worst case matrix C by adding a perturbation G, where each entry of this matrix G is a Gaussian with standard deviation sigma G, which is very similar to epsilon. Epsilon is the suboptimality of the solution that we are looking for. So that's it. So we just need to perturb our cost matrix, and now we can try to solve this optimization problem. So the main result that we show here is the following. We say that suppose you are given any penalty version of this SDP, we need to assume that this SDP is compact. This is just a technicality, and it sort of holds for most of the interesting SDPs that we are looking for. And let's say we set the rank of this matrix U to be root m times log n. So we are setting the rank to be log n factor larger than what we really need to. In that case, what we show is that every approximate second order stationary point of this perturbed SDP will correspond to a global optima of this original problem. That is, we might find multiple SOSPs here in this problem, but all of them will be close to a global optima. Okay. So what that means is that by using certain nice and recent results for figuring out second order stationary points for non-convex problems, we'll be able to provide a epsilon approximate solution to this problem in this much amount of time. So here, this factor 1 by epsilon to the power 1.75 is the number of iterations. Here I'm hiding some problem dependent constants. And per iteration, the complexity is given by this, where Z is the number of non-zeros in the entire system. That is, number of non-zeros in our constraint matrices as well as the cost matrix. And for various practical problems like, say, max cut, etc., the value of Z can be much smaller than n square. Okay. So what this says is that our per iteration complexity can be very nice and can be much smaller than, say, per iteration complexity of standard interior point methods. On the other hand, the number of iterations that we might need to take can be much larger than that of interior point method. And another method which is completely in the opposite end is multiplicative weights update, which takes almost optimal per iteration complexity. But the number of iterations for this method can be very large, especially it depends on a width parameter, which can have some hidden dependence on the number of constraints as well as the dimensionality of the problem. Okay. So so at a high level, the proof of our theorem goes through two key results. So the first result is that every approximate SOSP of the perturbed problem is approximately rank deficient. That is, we find any SOSP or approximate SOSP of the perturbed non-convex optimization problem, and it will be close to being rank deficient. And second result that we have is that, which is sort of standard in this domain, is that approximate rank deficiency of our stationary point implies close to being global optimal solution. Okay. So if we instantiate our result for a concrete problem, that of, let's say, matrix completion, then we get some very interesting result. So matrix completion is a problem where the goal is to approximate or find out this matrix M as much as well as possible using a few samples omega that you observe from this matrix M. So typically, the way to solve this problem is to add a small nuclear norm regularization. And this problem can be rewritten as an SDP. So what we show is that no matter what matrix M or this index set omega or how many entries do you have in the index set, it doesn't matter. We'll still be able to solve this problem optimally in polytime with rank guaranteed to be at most root M times log n. On the other hand, the existing results can provide solution which can have much lower rank. In fact, they can provide even solution which are of rank 1 if the underlying matrix is of rank 1. But they will need some stringent assumptions on matrix M as well as the set of samples that you are observing from this matrix. So in summary, we have been able to come up with an efficient algorithm for solving SDPs with small number of constraints. We require our SDP to be compact. But by using some standard smooth analysis type of formulation and using standard non-convex optimization algorithms, we can show that our algorithm will converge to an approximately optimal solution in small amount of time. For future work, one big direction that we are looking at is how to reduce this dependence on the rank parameter on log n. That is, we want to get it back to the optimal root 2 m. Furthermore, we have been looking at penalty version of this problem, but one can also ask this question that, okay, what if you use augmented Lagrangian method to solve the problem? Then how does this entire machinery works? And solving that question will be very interesting. That's all I have.
Great, thanks, Prateek. Maybe a quick question while the last speaker sets up.
Yeah.
Yes, please, in front. Yeah.
You said in the matrix completion context, you can't guarantee a low rank solution. In experiments, does it indeed have high rank, or are you generally picking up something low rank when the ground truth is low rank?
So we can guarantee a rank to be root m, which still is like, sublinear in n in general. But in experiments, yes, like especially if the data is generated the way other matrix completion solutions require it to be, then the rank turns out to be very small. It turns out to be almost constant.
Great, well, let's thank Prateek again.